Welcome back. So the last time we saw a few examples of the chain rule. In particular, we were looking at paths, and we were talking about using two different ways to describe the same geometric object. Let's say this one and this one. These two represent the same geometric object, and if you take a function f equals x square minus y square and g1 is f of r1 and g2 is f of r2, yeah, we computed these derivatives. G1 dash was minus 60 and G2 dash was minus 24t. So if you take the same value of t, you will obviously get 4 times the number. But that's not the correct thing to do, right? The correct thing to do is to look at the same value of x comma y, right? So if you want to compute, if you want to know how fast f is changing according to one particle at this point, you have to compute the rate of change of f according to the other particle at the same point. But even then, you will get different answers, right? So this concept of the rate of change depends on the path, not just the geometric object, which is the curve. Now the point is, there is, for regular paths, there is a very nice way to parametrize the curve. That's called the arc length parametrization. So what you do is you define a new parameter. So you define this. Okay. Perhaps I'll call this, maybe I'll call this S of t, and I'll put a t here, right? This is the so-called arc length of a path. Okay. So this based here is non-zero because we assume the path is regular. The norm of it is a continuous function, and you integrate this. I mean, I'm assuming you know one variable integration rigorously. So you get a function of t, right? By the fundamental theorem of calculus, this function's derivative is the speed, and this is not 0, right? At this juncture, there is something called the inverse function theorem, which we will look at later. But the bottom line is, if you define g as f of r of s, right? By r of s, what I mean is t is a function of s. Here you're giving s as a function of t. The claim is you can solve, you can invert it and find t as a differentiable function of s, right? And dg ds, what is that equal to? That is precisely equal to gradient of f r dash divided by this. This is the claim. I won't prove it now, right? We'll look at this sort of a thing later on, but just to foreshadow these sorts of things. So the point is, this is the place where dg ds comes from, and this is the same for g1 and g2. That is the utility of it. Okay. Anyway, let's move on. The point of this little comment was to just convince you that the chain rule can be used to do very interesting things, which have ties to geometry, right? So let's look at one more example, right? So let f from R2 to R be a differentiable function such that the gradient of f is not equal to 0 anywhere. Let c be a constant such that f of x comma y equals c describes a differentiable curve having a well-defined unit tangent vector at each point. Okay. I am being a bit vague here deliberately. This is again, this is something we will look at later, but it's good to see this beforehand once. So when I say differentiable curve, what do I mean here? I mean that the curve is simply a geometric object in R2. I am saying it's the image of a path R of t which is regular, and so it is differentiable and it's regular, so it has a well defined unit tangent vector at every point, right. So it has a well defined unit tangent vector. What does that mean? That means that you can divide by the derivative of the velocity. I mean that's where this assumption is used. Okay, that's what this means. So in other words, what we are saying is so this is what we mean by this set of hypotheses. Yeah. Right. So what we can prove at this using this set of hypotheses is that the gradient f is normal to this curve. Meaning if you look at this curve in R2, the gradient points perpendicular to it. What does that mean? It means that it is perpendicular to the velocity. Indeed, if you take, suppose you take f of r of t, we have assumed that after all this path, this is a differentiable path. It's the image r of t where r dash is non-zero. So d by the chain rule, this is the gradient of f at the point r of t times the velocity vector, right? But f of r of t is identically equal to c for all t, which means df dt is 0. So this is equal to 0 for all times, and therefore this gradient is actually perpendicular to the velocity, right? Okay, that's one point. The next point, if you wish, is df ds, which we have defined to be this. The so-called directional derivative along the curve. What is this equal to? This is identically 0, right? So f does not change along the curve. This is easy. Now the directional, if you compute the directional derivative of f along any vector on C, this is equal to this, right? This is less than or equal to gradient of f with equality if and only if v equals gradient of f, right? Let's say the times lambda where lambda is positive, right? This was the Cauchy-Schwarz inequality, right? So meaning the directional derivative of f is highest when along the normal to the curve. Indeed, the curve is a place where f is a constant. These are sometimes called contour lines. If you've done geography, you will remember this. F is a constant, and the fastest way to increase f is to go perpendicular to these contour lines. Okay? So again, this is just to illustrate the chain rule to do something interesting, but I do realize that we've not really took any serious effort to define these things carefully, okay? But we will look at these things later. Right. So that sort of finishes our discussion of the chain rule for now. That the chain rule is extremely important, as you can see, right? So I hope you can do some problems just to gain practice with how the chain rule works in multivariable calculus. Right. The next order of business is to look at higher order derivatives. So in one variable calculus, the derivative of a function tells you how fast the function is changing. The second derivative tells you how fast the slope is changing. Physically, what would it mean? The derivative is like the velocity, the second derivative is like the acceleration, right? So do higher order derivatives play a role in real life? They absolutely do. Most partial differential equations are more than one order. They involve second order derivatives or third order and so on. But even, for example, in the context of AI and ML and optimization, especially, these things play a role. We'll look at that later. So first of all, how does one even define differentiability more than once, right? So suppose f is a function, let's say it's differentiable, and you get the derivative. You can ask, is x going to the derivative of x, right? Is x going to the derivative of x a differentiable function in its own right? What would that even mean, right? X is in Rn, the derivative of f is an m by n matrix, right? And we have been treating matrices, we can treat them as simply vectors in Rmn. Instead of writing these as a matrix, you can simply write all of these entries one after the other, right? So you can simply ask whether this function is differentiable or not, right? So that if that is true, then you say f is twice differentiable at x. So for this you need to be a tad bit careful. So first of all, differentiability makes sense only on open sets for us. So first of all, we would assume that x is an interior point of the domain of f. Yeah. Secondly, this function must be differentiable on a neighborhood of x, not only at x. Otherwise, how can you take two derivatives, right? Thirdly, if you take df of x, right, the image of this function in Rmn must contain a neighborhood of df of x. Otherwise, how can you talk about differentiating this function further, right? It's not possible to do that. So we would want to make several hypotheses for this to make sense. But if all of these make sense, then this is, if the answer to this is yes, then f is said to be twice differentiable. And if it is twice differentiable, you can talk about the derivative of the derivative. That will be a more complicated object, and you can talk about thrice differentiability and so on and so forth. But while all of this is perfectly fine, we would want to look at this in greater detail. Here is an example of a function showing how things can go wrong. Yeah. So suppose you take this function when xy is not 0, 0, and say it is 0 when xy is 0, 0. Yeah? Okay, so the question is, first of all, is this, what can we say about this function, right? Obviously, this is a rational function, right? So it is, of course, C1 on this region, on the domain. So it is differentiable, of course. You can take its partial derivatives. So fx. How do you differentiate this? Well, you, as always, you hold y to be a constant and you differentiate this. So you get y times x square minus y square plus x times y times 2x times x square plus y square minus 2x times xy x square minus y square divided by this when xy is not 0, 0. Yeah? So what is this equal to? You can write a formula for this. This is, of course, equal to y times x raised to 4 plus 4x square y square minus y raised to 4 divided by x square plus y square whole squared, provided xy is not 0, 0. Now, is the function, does the partial derivative exist at 0, 0? Sure it does at at 0, 0. What is the partial derivative? Does it exist? Well, it's simply limit as h goes to 0, f of h comma 0 minus f of 0, 0 divided by h. But when y equals 0, this is automatically 0, this is 0. So the partial derivative is 0. Okay. Now, as x comma y goes to 0, 0, what can we say about fx? Right? The claim is this is actually equal to 0. Right? How does one prove such a claim? Right? This is not obvious. Yeah. So how do you prove such a claim? Well, there is a, before we do this, before we prove said claim, we can also differentiate with respect to y. We can use the usual quotient rule to differentiate with respect to y, and it will turn out that this is equal to y raised to 4 plus 4x square y square minus x raised to 4 divided by x square plus y square square. Why is this so? Again, please actually differentiate and verify. As we shall see, it's not, at least for saying one thing, it's not immediately important to know what the precise value of the derivative is, more the form of it. What we want to say is this is when xy is non-zero. What of the case when xy is 0? Its limit as h goes to 0, f of 0 comma h minus f of 0, 0 divided by h. This is 0. What about f of 0 comma h? Well, if you substitute x to be 0, you'll get 0. Okay, so happily enough, this is 0. Now the claim is limit as xy goes to 0, 0, fy of x comma y is 0, which is fy of 0 comma 0. Let's assume these claims for the moment. That would mean f is C1. What is C1 again? C1 means the partial derivatives exist and they are continuous functions in their own right, which means f is differentiable, which means f is also continuous. Right? So f is perfectly well behaved. Okay, we have to still prove these, why are these two facts true? You'll have to prove these. Let's move on and let's return to this a little later. Right. Now, the point is, if you look at this function, the partial derivatives, what are the partial derivatives? This partial derivative is also a rational function. Yeah? So, rational functions are of course differentiable whenever the denominator is non-zero. So, surely d by dy of fx and d by dx of fy exist when xy is not 0, 0, right? This much is certainly the case. What if xy is 0, 0? Let's see what will happen. So, if you want to compute the derivative of this with respect to y, right? So, d by dy of fx at 0, 0 would be what? Limit as h goes to 0, fx of h comma 0 minus fx of 0 comma 0 divided by h. This we have agreed is 0, right? Now, what is fx of h comma 0? So, when y equals 0, what do you get, right? You get when y, so when, sorry, this is 0 comma h. I'm sorry about this, because it's d by dy, right? So, it's 0 comma h. So, when x is 0, what do you get? When x is 0, this term goes away, this term goes away, this term goes away. So, what are you left with? H times minus h raised to 4, which is minus h raised to 5 divided by h raised to 4. So, it is minus h raised to 5 divided by h raised to 4, which is minus h. And that h cancels out with this, and you will get minus 1, right? What if you want to compute d by dx of fy? What is this? This is the limit as h goes to 0, fy of h comma 0 minus fy of 0 comma 0 divided by h. This we have agreed is 0. What happens when y is 0 here? This term goes away, this term goes away, and so does this term. So, what are you left with? Minus x times minus x raised to 4, which is instead of x you have h, minus h times minus h raised to 4, which is plus h raised to 5 divided by h raised to 4. So, which is h raised to 5 divided by h raised to 4, which is h itself, right? So, this is simply h divided by h, which is 1. And that is not equal to minus 1, which is equal to d by dy of fx at the origin. This is the problem that I was alluding to. Your function is perfectly reasonable. It is C1. The partial derivatives, the second order partial derivatives exist too. Yet, if you take the mixed ones, that is, if you take d by dx first and then d by dy versus d by dy first and then d by dx, you can potentially get different answers. Okay? That is the problem. Now, in case you are wondering whether this is a mere technicality, it is not. For example, if you are familiar with chemistry and thermodynamics, it's very crucial that these mixed partial derivatives be equal to each other, right? And that's not the case here, right? So, for a perfectly reasonable function, the mixed partial derivatives need not be equal. But now let's return back to why this is C1. Why are these claims true, right? I'll do one of them and I'll leave the other one as an exercise for you to do. Okay, please think about it. Okay, this would require some thought from your side. So for example, let me do the one for, let's say, fy, right? Limit as xy goes to 0 of fy, which is what is this? What is fy equal to? Let me write this once again. So it's okay. So how does one compute this limit? So notice that it is easy to prove limits don't exist if they really don't by simply choosing two of your favorite paths and hoping that you'll get different answers. The question is, point one, how do you prove that these limits exist? Point two, how would you even guess whether they would exist, right? This is not obvious. For all we know, we would have guessed that it didn't exist, and we would have spent a lot of time and effort trying to prove it using different paths and finding the same answers over and over again, right? So one way to do this is as follows. This is not foolproof, but it works. So suppose I take x equals r cos theta, y equals r sin theta, right? And what's this equal to? This will be minus r cos theta, it's r raised to 4 cos raised to 4 theta, 4r raised to 4 cos square theta sin square theta, minus r raised to 4 sin raised to 4 theta, divided by r square cos square theta plus r square sin square theta whole square, right? What is this? This cos square theta plus sin square theta is 1, so this entire thing is simply r square. So this raised to 2, the denominator is therefore r raised to 4. You can pull out the r raised to 4 from here and cancel it out. So this is minus r cos theta, cos raised to 4 theta plus cos square theta sin square theta minus sin raised to 4 theta, right? So mod of this equals the mod of this. Mod is of course larger than 0. This is less than r, the mod of cos theta is less than 1, plus the triangle inequality, right? The mod of cos raised to 4 theta is less than 1. This is certainly less than 1. This is also less than 1 for sure. So this is less than 3r, and so which is equal to 3 times square root of x square plus y square. This goes to 0 as xy goes to 0, 0. Why does this go to 0? Again, how would you prove that? Surely this being a polynomial is continuous. Square root of a continuous function is the square root function is continuous, and the composition of these two is continuous. So as xy goes to 0, 0, this goes to 0. So by the sandwich rule, we can conclude that the mod of this goes to 0, and hence this itself goes to 0. This is a way to also guess at the limit. I mean, so suppose, roughly speaking, if you use polar coordinates, this will be roughly like r raised to 4, this will be like r raised to 4, this will be like r raised to 4, and this is also roughly like r raised to 4. So the r raised to 4's cancel out, and this, roughly speaking, goes to 0. That's how you would guess. Okay. So the correct thing is to, of course, at the end of the day, you have to come back to Cartesian coordinates because the limit is in Cartesian coordinates, right? So I'll leave the other one as an exercise for you to do. But anyway, the point I'm trying to make is that the mixed order partial derivatives, the point is fxy, which is d by dx of d by dy of f, and fyx need not be equal. Okay? So we'll have to define a condition under which they can be proven to be equal. Okay? That will be important for us. All right, so let's stop for now. So we'll continue with proving the condition under which these two things will be equal and proceed further. So yeah, let's stop. Thank you for joining.